Alexa, that's not where you do chemistry. Alexa, that's not where you do chemistry. Alexa, that's not where you do chemistry. Three. Okay. Alexa, that's not where you do chemistry.
A redox reaction happens when electrons are transferred between atoms. When this happens, one reactant is oxidized and one is reduced. When a molecule loses an electron, it is said to be oxidized. When a molecule gains an electron, it is said to be reduced. One way to remember that is Leo says grr, me and Dina like oil rig, which is oxidation is loss, reduction is gain.
We can find oxidation states using an individual and total chart. The first step is to determine the overall charge of the molecule and write it in the box on the bottom right. The second step is to assign an oxidation number of -2 to oxygen, and then to assign one of +1 to hydrogen. Then you divide by the total charge by the number of atoms. For example, a +2 total charge of hydrogen divided by 2 hydrogen atoms equals an individual charge of +1. For some molecules, figuring out the oxidation number is like a puzzle. For chromate, we know that the total charge is -2. We can figure out the oxidation number for chromium because we know the charge for an individual oxygen is -2. Then we can do some simple math and find that the charge for chromium should be +6. Since we only have one chromium, the individual oxidation state must be +6. Here are some exceptions to the usual oxidation states rule.
Displacement reactions happen in a reaction between a metal and either an acid or a metal salt. They are called displacement reactions because the ion in solution is displaced through the oxidation of an element. Metals can also be oxidized by aqueous solutions of various salts. Iron metal, for example, is oxidized to Fe2+ by aqueous solutions of Ni2+. We can predict whether a certain metal will be oxidized by either an acid or a particular salt using the activity series. The higher on the activity series a metal is, the more easily oxidized it is. Any metal on the list can be oxidized by the ions of the elements below it. Glycerin, which is sometimes called glycerol, to potassium permanganate. It is unnecessary to have exact measurements when doing this experiment. Just use a scupula to make a small pile of potassium permanganate on a piece of tinfoil or directly on the hood. Then create a small indentation in the pile with the scupula and use a disposable pipette or dropper to add a few drops of glycerin to the pile. Because glycerin is the limiting reactant, the more glycerin that is added, the bigger the reaction and therefore the fire will be. We had some issues with our first few tries of the experiment because the fire took a really long time to start, which is probably because the potassium permanganate was too old. We did it again with a lot more glycerin and some newer potassium permanganate, and it went much faster, although it still took several minutes to start.
The rate of the reaction is faster the more glycerin is touching potassium permanganate, which is why we put glycerin in the center of the pile. Potassium permanganate and glycerin is a redox reaction. In this case, potassium permanganate is reduced and glycerin is oxidized, which we figured out by finding the oxidation states. There is a slow rate of reaction because the glycerin absorbs much of the heat generated. The reaction creates a lot of heat, which is why it generates a bright flash of sparks. Once it starts to smoke, the smoke helps carry away the produced water and carbon dioxide, as well as any waste carbon produced in the burning of glycerin. Then, when it ignites, the whole pile will react quickly, having a large amount of extra heat to push the reaction along.
This is us figuring out the oxidation states for the reaction in our experiment between potassium permanganate and glycerin. In this one, manganese goes from +7 to +4, so it is reduced.
Alexa, this is where you do chemistry.